we'll try to understand what are semiconductors and how these semiconductors are useful for our daily life. For example, we are using the LED, light emitting diode. So, what this semiconductor is? We know semi means half or partial. So, this partially conducts and therefore it is called as semiconductor. Now, the question is why it conducts partially and under what condition these semiconductors conduct. Let us try to understand the basic structure of semiconductor by taking the example of silicon. So, silicon is a material element with atomic number 14 and therefore the electronic configuration will be 1s2, 2s2, 2p6. So, this becomes 10 and then 3s2 and 3p2. Now, these four outermost electrons, they will create or they will just s and p orbitals get mixed up as sp3 hybrid orbitals. So we will have total 4 sp3 hybrid orbitals, and we have seen in previous class that these 4 sp3 hybrid orbitals are in the shape of tetrahedron. And this tetrahedron is nothing but a perfect shape samosa. You might have tested it a number of times, but that is the perfect shape samosa is called as the tetrahedron. And these 4 electrons in the outermost orbit will be here with these 4 orbits, and each orbit is sp3 hybrid orbital. This is called as hybrid. Now, it is very difficult to draw this kind of structure every time. So we'll have a simpler structure, but we know that there can be another silicon with another sp3 hybrid structure, and the electron from this silicon and this silicon will pair with each other and they will form the sigma bond. Sigma bond is a very strong bond. Similarly, here also, here also, here also. So every electron in the sp3 hybrid orbital of silicon is combining or the sharing electrons with other uh, silicon atom. So in planar structure, of course, this structure is not planar, but we'll just show it in this way. Now these are not double band bonds. This one line represents one electron from this silicon. Of course, this is one electron from this silicon, one electron from this silicon, one electron from this silicon. So this one atom of the silicon has the 4 electrons, and the remaining 4 are coming from the sharing of the electron. So the silicon other atoms are sharing. So they are forming the silicon single bond, not double bond, single bond. This is a covalent bond. Okay. Of course, this silicon will also have sharing of electron, and this also has sharing of electron, and it is a very complex structure, very complex structure. Okay. So just to make simple, we are just showing it in planar structure with these two lines, but these are not the double bonds. Now, how does this conductivity increases? There are two ways. Either you break the bond and release the electron, and this electron will move throughout the material, and since electron is moving, we will have the conductivity. But this conductivity is very less. This is called as intrinsic semiconductor, as we have seen in previous classes. So what we do is we add some material inside this structure. So instead of now simple silicon structure, we can have two different type of impurities, either donor impurity or acceptor impurity. Now, what is meant by donor and what is meant by acceptor? Donor is the impurity, of course, in pure form. The donor atom can donate the electron. It can give the electron. whereas this acceptor impurity will accept the electron. Okay. So how does it happen? For example, in case of donor, we have the one of the atom. The simplest example is phosphorus, and the electronic configuration will be 1s2, 2s2, 2p6, 3s2, and 3p now 3. So out of these 5, the 4 electrons will combine with the silicon like this. There are 4 uh, electrons of the phosphorus and 4 electrons of silicon. So this structure is formed. But there is another extra electron of phosphorus. Remember, this electron is of phosphorus. The phosphorus has 15 electrons and 15 protons. We can write here 15 electrons and 15 protons. So obviously the combination of these two will be neutral. So even if you are seeing the extra electron, it is not going to give the negative charge on the phosphorus. This structure is at this moment it is neutral. When this electron will go out, then it will become positively charged ion. That we'll see. And there is another impurity called as aluminium. Now aluminium has only 13 electrons total, and therefore the aluminium 13 can be written as 1s2, 2s, sorry, 2s2, 2p6, 3s2 and 3p1. So there are only 3 electrons in the outermost orbit. So it cannot form the, uh, just a minute, we'll have to just delete one of them. Okay. It cannot form 4 bonds, it can form only 3 bonds, and there will be one electron coming from the silicon, but there is no electron from the aluminum. So this is a vacancy. This is a vacancy. But remember, again we have total the 13 electrons and 13 protons. So again this structure is also stable. It is neutral, electrically neutral. There is no charge on the aluminum. Now this vacancy is named as hole, but there is no hole as such. There is only a vacancy. There is uh, a space where the electron is absent. So absence of electron. Now let us consider that this electron is removed from here somehow. So of course, because this electron has higher energy than the other electrons are bound. This electron is free, so it can move away, and this phosphorus can become now positively charged particle. Positively charged ion, and the bonds are as it is. And now this electron somehow can go to this vacancy, and since there is a vacancy, you can have this aluminium with extra electron. Now the aluminium has 14 electron, 1 electron extra. So the charges, total charges will be 13 proton and 14 electron, that is negative. So this will form a negative ion. So this let me show it by a box, okay, like this, because ion will not move anywhere, and we'll have these bonds like this: silicon, 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 and silicon on all sides. Okay. Now with the transfer of the electron, we can have the positive phosphorus ion and negative aluminum ion. Now we'll see what happens when we consider the p-n junction diode. And of course this impurity, because of the uh, donor impurity, we have this as n type of impurity because it is giving the electron, and p type impurity which is giving the less electron, or it is taking the one electron and creating the holes. So let me draw this picture once again. Now this is p-n junction. I will take left hand side as n and right hand side as p, and this is the boundary of this p-n junction. So this is n, this is p. Now in n we have large number of phosphorus atoms, okay, before it gives out the electron with one electron. phosphorus with one electron, phosphorus with one electron. On the other side of this p type, we have aluminium with hole and aluminium with hole, another aluminium with hole. Now what can happen? This electron can go here, and let me draw the structure like this. One of them I will just show. Just a minute. Okay, let me draw it here only. So this, oh, okay. So we have this structure, and let me draw. This electron is going from, say, phosphorus to aluminium, so phosphorus becomes positive ion, and aluminium becomes negative ion. So we can just extend this structure, and I can just show something like this, that there is a positive ion and on this side, and negative ion on p side. Remember, the positive ions are on n side and negative ions are on the p side. Now, if there is another, say, aluminium, another level, another, say, layer of the atoms, so this electron may try to go towards this aluminium. But now, since there are 3 or 4 levels of atomic layers which are formed because of the transfer of electron, now the more transfer of electron is not possible. So this electron is rejected by these negative ions. And similarly, we can say that this hole is also repelled by these positive ions. Of course, that is not true, but we can say that, considering positive as positively charged particle, which is not, but it happens. Now, what is the meaning of this? The meaning is, it is similar to, this is positively charged wall of ions, and this is negatively charged wall of negative ions. So these two walls will be having potential, say, positive here and negative here, and therefore, of course, these are fixed, these are not moving, these are immobile, which are not moving, immobile. So immobile means they are not moving charges. And what are the moving charges? They are where holes and the electrons, they are depleted. Depleted means they are removed from this region, and therefore this region is called as depletion region. Of course, since it is a barrier of potential, the electron is not ready, it is not, sorry, the electron is not, it is not possible for electron to cross this barrier, and therefore it is called as potential barrier because of potential. It acts just like a battery. So this is a positive terminal of the battery, this is negative terminal of the battery, and unless you add some higher potential. Now, if the electron is attracted toward this higher potential of external battery is something like this. We know what are the 1.5 volt and so on and so forth. Okay. So that battery positive potential is connected here, and suppose this negative terminal is connected here. So the negative terminal will push this electron on the right hand side, and right hand side is, you can see here, The right hand side we have taken as P and the left hand side as N. So this is N region, this is P region. The P region is connected to positive terminal of the battery, N region is connected to negative terminal of the battery, and you know that this is the forward bias. So if the potential of the battery is less than this barrier potential, so electron will not be reaching to the positive terminal of the battery, because electron will not get enough force of attraction. But as soon as this battery potential, suppose considering this battery is variable, as we increase the battery potential, what will happen? When this becomes equal or this battery potential becomes slightly more, the electron will get attracted. And as the electron moves through the circuit, the current will start flowing. So you can just measure the current just like previously we have seen. We can add the ammeter here. Okay, and then when the battery potential is slightly more than this, or when we keep on increasing the battery potential more than the potential barrier, more and more electrons will come from the N region to P region and the current will flow. Now what will happen if we plot the graph of this? And how we can plot the graph? Again, previously we have seen that the voltage is independent variable, so it should be on, say, x-axis, and the current will depend. So as we increase the voltage, we will get the current. Okay, so we know that the voltage is independent variable, and therefore as we increase the voltage, the current will increase. But there is a catch here. Now the battery potential, suppose it was 0 initially, so there was no current because the electron was not able to cross this potential barrier. Now slowly we increase the battery potential. If the battery potential is still less than this depletion region, and the potential of this depletion region is, for example, 0.7 volt for silicon. Okay. So for silicon, unless this battery potential is equal to 0.7 volt or more than that, there will be no current. So consider this as 0.7 volt and there is no current. So therefore you get absolutely no current. And as this potential increases above the 0.7 volt, linearly, almost linearly, the potential will increase. And if you increase the potential very high, then suddenly the current will start increasing. This is where the current will start increasing without increasing the potential. Okay, that is a dangerous situation. So you should stop. You should stop the observation at this point only. So mostly this is a linear region, and this is what is called as the diode diode characteristic. So what do you mean by diode characteristic? Diode characteristic is the plot of current and voltage, and as the voltage increases, how the current is changing. Initially it will be 0 up to 0.7 volt, and then it will start increasing. Now this is about the forward bias. Now what about the reverse bias? We'll go for reverse bias and then we'll stop there. So in reverse bias, what we do is, now I'll just draw only N and P region. Now we know that there are holes in P and the electrons in N. And now we are connecting this N region with positive terminal, whereas the P region with negative terminal. And of course this potential is very high. So what happens here? And then we'll just put some ammeter here. Now in this case, there are electrons here, there are holes here. Now electrons are not attracted towards the negative terminal, where they are attracted toward the positive terminal of the battery. Now this electron is moving away from the potential barrier, and therefore the potential barrier will be increased. more and more. Okay. So the size of the potential barrier increases. It is more than 0.7 volt now. Now the battery is connected in such a way that the electrons are going away from the junction. Now if the potential is very less, now we have this negative potential. So the x-axis is negative, and of course the current is also negative, and therefore y-axis is also negative. This is the y-axis current. Now when we are giving the voltage slightly less, then the current is very less because of this very small number of electrons. Okay. And very small number of electrons will be generated here as minority charge carrier, and holes here as minority charge carriers, and these electrons, very few electrons will get attracted towards this positive terminal of the battery, and they will be able to cross this junction. So the current is very less. It is in microampere, okay? And in forward bias it was in milliampere. But what happens if the electron is suddenly moving with very high potential? Now here it can get attracted very quickly. Okay. Even though there is a very high potential, this electron can strike on other, say, phosphorus atom or the silicon atom, and then it can create more electrons. It can take out the electrons, and this is called as the avalanche. So one electron will strike on the one atom, it will create two electrons. Now these two electrons are moving very quickly, very fast, very high speed, and they will strike on the other atoms. So other atoms will also give out the electrons, and thus the number of electrons will increase. And when this position comes, the current, because number of electrons are moving, so current will suddenly increase. Now, if you don't stop this, then it can heat up the PN junction diode, and it will break. Okay. So basically, this is called as breakdown. So we have two types of breakdown. One is the avalanche, and the other one is Zener breakdown. We'll see Zener breakdown separately. But remember here that whenever there is a breakdown, the voltage is almost constant. We are not increasing any voltage, battery voltage. Okay. So this is breakdown voltage, and the current is suddenly increasing. So you can see the current was almost zero here, and now it has increased to a large extent. So this is a reverse bias characteristic for the diode. In general, what we can say is that the forward bias, the current is increasing with the voltage quickly. This is voltage, this is current, this is voltage. And in reverse bias, it is almost no current, almost no current. So up to this position. So this is on, diode is on, whereas diode is off in reverse bias. So that is how we can draw the characteristic, and of course, depending upon these regions, we resistance offered by the diode. Obviously, resistance in reverse bias will be very high, because we know V is equal to IR, and therefore R will be equal to V by I. Now here the voltage is very high, but the current is very less. Okay, and therefore R value will be very high. Whereas in case of PN junction forward bias, here, so I by V will be, so sorry, V by I will be resistance. So as we are increasing the voltage, we are getting the current. So the resistance is much less. The forward bias resistance is very less. It is in ohms or a few kilo ohms, whereas in reverse bias it will be always in kilo ohms.